All right, we're back with a little bit of extra charge here. I think we're now at like 20%. Anyway, still talking about some coordinate proof ideas. In example 7, we have a square which has vertices at 0, 0, m, comma 0, and 0, comma m. Find the fourth vertex. So maybe you can visualize what this looks like in your head, or maybe you need a little bit of a picture to go along with it, like so. What would be that fourth vertex? What would be the coordinates? Well, if it's a square, all the sides have to be the same, and they have to be perpendicular sides. So that fourth vertex needs to be m, comma m. All right, let's take a look at the next example. So in this next example, this is going to be our first like true coordinate proof. The one that we did back in the first objective, it kind of was, yeah, but it had specific coordinates instead of variable ones. Example 8, find the missing coordinates to show that the statement is true. So the statement here is that segment PT is congruent to segment RS, SR. Look at those two segments in the picture. What kind of segments are they? Are they midsegments? No. To be a midsegment, that would have to join up S and T, but it's not. These are a different kind of segments. These are called medians, which we discussed in a previous lesson. All right, let's look at this picture in a little bit more detail. So yeah, we can see that because these two are congruent, S has to be a midpoint. And then likewise, because, whoops, these two are congruent, T has to be a midpoint, doop-a-doop, right? And if you connect a vertex to a midpoint of the opposite side, these type of segments are called medians. So here it looks like we're trying to show that these medians are congruent to each other. For what kind of triangle? What kind of triangle is this? I know what this triangle's missing. Color. Wouldn't you agree? I mean, now it's so much more pleasant instead of all this like black and white colorless stuff. All right, there we go. What kind of triangle is PQR? Look at the coordinates. Look at each one of the vertices and how it's labeled. We've got the origin at P, and R is at 2h, comma 0, and Q is at h, comma k, which puts H right here in the middle, making this thing an isosceles triangle. So this thing is isosceles. If I can spell it, it's impossible. Oh, I pulled it off. All right, so this isosceles triangle is very similar to the one that I made, like right here, except for what that one does on exercise 8, it just basically takes this B and makes it 2 of them, and then this one just makes it 1, so you don't have fractions in each one of your vertices, which is kind of handy. All right, so let's write ourselves a given statement and a prove statement. We just discussed that this thing is an isosceles triangle. So I am going to state this thing as an isosceles triangle. So we're going to say given isosceles triangle. Look at that. I did that without like the very first time. Triangle PQR. And let's say that S is the midpoint. This is very similar to what we did on that first one. S is the midpoint of PQ. And then also T is the midpoint of QR. All right, and notice I didn't actually assign my coordinates here. I'm going to assign those coordinates actually within the proof, as we'll see here. And then what I'm trying to prove is this statement that's just like right there. We're trying to prove that PT, that segment PT, is congruent to SR. Well, one of the ways that we proved something like this in the last unit was the idea of congruent triangles and using like CPCTC. So here's another way to tackle something very, very similar. In the coordinate plane, in order to show that segments are congruent to each other, we usually use the distance formula. But before I can use the distance formula, of course, I am going to have to get the coordinates or points S and T. So for those, we'll have to use the midpoint formula. All right, so all the stuff here in pink, it's not part of the proof. It's just me mapping out what it is that I'm going to have to do in order to actually carry out this proof. All right, so step number 1, for this isosceles triangle, we're going to assign some coordinates. So we're going to say, let isosceles triangle, why is that capitalized? I don't even know. Triangle P, Q, R have coordinates. One too many O's. Coordinates. Let's see, P is at the origin. Q has Q has H, K. And R is at 2, H, 0. All right, so if we're using the coordinates or points S and T within this, we need to actually find them, and the way that I'm going to find them is with the midpoint formula. So I'm just going to state that out. So by the midpoint formula, so this is kind of the reason that we would put usually within the 2-column proof. Sometimes you could put it afterwards, or you could put it before it. I just think that it flows a little bit better if we put it before it and we say exactly what it is that we're using here. So by the midpoint formula, now actually use it. Let's find the coordinate first for point S. So S, midpoint between Q and P. H plus 0 over 2 and K plus 0 over 2, which will simplify to H over 2 and K over 2. Fractions. We love them. All right, let's do the same thing for T. So for point T, we're taking the average of R and Q. So we'd have 2H plus another H divided by 2, and a 0 plus a K divided by 2. That's a K. Take my word for it. So T simplifies to, I'm going to have 3 H's, 3H over 2, and another K over 2. All right, so I got the coordinates for each of these using the midpoint formula. And again, I don't actually have to highlight this, but I'm just going to point it out that that's what we used. And now I'm going to use the distance formula in order to show that these two segments are congruent to each other. So I'll state it again by the distance formula. And now actually use the distance formula on S and T. And then separately on, not on S and T, that's the midsegment. Which one I want to use? It's these two, it's PT. There we go. Let's do PT first. PT involves 0, 0, so it should be real easy. And then just for a matter of convenience, I'm going to write this on here. So 3H over 2, K over 2. And then over here at point S, it was H over 2, K over 2. All right, so this one is first. Boop. I'm going to find its length. Subtract the x's, square it, subtract the y's, and square it all within a square root. So big old square root. Who knows how long it's going to be? That might be long enough. So I've got 3h over 2 minus 0, which we're squaring, plus k over 2 minus 0, which we're also squaring. Well, look at that. I made it just a little bit too long. That's okay. I can fix that. I can fix it. Guys, stop panicking. There we go. All right, so now we want to simplify it. Subtracting 0 does a whole bunch of nothing to each one of these coordinates, and I would have 3h over 2, which we're going to have to square, plus a k over 2, which we're going to have to square, and it looks like I made it too long again. Maybe I should just do that part second instead of first. Hard habit to break. Okay. So whenever I square the stuff inside the parentheses, both parts get squared. So it's 9h squared over 4 plus k squared over 4. And I can just leave it just like that. I can't simplify. I could get a common denominator, which is 4, which I already have, and then maybe simplify the square root a little bit, but I don't have to. If I'm going to show that this segment is congruent to SR, I just need to show that the other one simplifies to exactly the same thing, right? So that's what we're going to do next. And then also to give this a little bit of color, I'm going to highlight that. Okay, so what did we say, SR? SR. Well, let's do roughly the same thing, and then this one gets a different color. It's going to get purple. Dang it. Will that look good? It looks... Yeah, it does. I mean, if that was on a shirt, I'd probably wear it once. Okay, square root of, we're doing S and R. So S, H over 2 minus R, 2 H's, squared plus, and then do the same thing with K over 2 minus 0, and then square it, and then shorten your square root because you always gotta. And then clean this thing up like you do. So we've got, I have h over 2 minus 2 h's. So I want to think of this as a common denominator here. A common denominator would be 2, so I multiply this thing by 2 over 2. It's 4 h's over 2. And I'm going to subtract away this h over 2, which makes 3 of them. And it's actually negative. Not that it's going to matter, because I'm going to square that thing in a minute. And then the other one does a whole bunch of nothing when I subtract 0. All right, now compare this already. It doesn't look exactly the same because you got that negative in there, but since you're squaring it, it's not going to matter, and we're still going to get a 9h squared over 4 plus k squared over 4, which means that they are the same length. So I'm going to draw that conclusion, and I'm going to say, since PT is equal to SR, PT must be congruent to SR. What allows me to go from one to the other one? Of course, it is by the definition of, there's an I in there someplace, congruent segments. And there you have it. There is your first official coordinate proof. What did you think? All right, so again, let's kind of recap here. We have coordinates, generic coordinates for vertices and for midpoints and stuff. We just used the midpoint formula in order to find the coordinates for the points S and T. And then we used the distance formula in order to show that those two particular segments were the same length, that they were congruent to each other. Now, this one could have been made easier. I mean, it was okay, but it could have been probably twice as easy if we didn't have fractions. How could I do this same exact problem? Because, you know, you always want to do a problem twice. How could I do this so that I don't actually have fractions? And the way that I do it is that I'm going to take each one of my coordinates and I'm going to double them all. So here's what I'm going to do. I'm going to copy this page and then paste it back in here. And then I'm just going to doctor this thing up. I'm going to see how this thing is going to look, boop, with new coordinates, more convenient ones, because I could have chosen them just a little bit differently. And I'm going to take each one of my P and my Q and my R and double each of these coordinates. And in order to do that, I need the white color and I need it obnoxiously large here, and then I'm gonna, oh, not quite that large, okay, maybe this one. I'm gonna color these out, and color this out, and maybe that whole entire thing, because I don't know if I'll have room. All right, and it was in black, so I'm gonna make it in black again. So this one was originally 2 H's. I'm gonna make it times 2, so 4 8. Technical difficulties. Okay, 4H, that's better. And then in order for this to be isosceles, I cut that in half, so it's going to be a 2H. And then since I doubled this one, I'm also going to double the y coordinate, 2K. All right, so whenever I come down here and I change each of these coordinates, I'm going to change them and make it obvious, so I'll change them into pink. So here and here, I've got, again, 2H and 2K, and then in here it's 4H's. All right, and now whenever I go to find the midpoint for point S, it is 2H plus 0. Throw a 2 in there, and it's also 2K plus 0. Throw a 2 in here. And so now whenever I go to simplify this, I have 2H over 2, which just gives me H. I have 2K over 2, which just gives me K. And look, no more fractions. They're all gone. All right, and then likewise down here at T, T was from the midpoint of Q and R. So instead of 2H and H, it's going to be a 4H and a 2H. And for the y coordinates, it's going to be 0 and 2K. Cram a little 2 in there. Okay, for the x coordinate, I have 4 H's plus 2 more is 6 of them. 6 of them divided by 2 gives me 3. 3 H's. And then 2K divided by 2 gives me just K. Look at that. Again, no fractions. All right, and then instead of actually like trying to fix all of that, I'm just going to delete it. Just going to completely delete it. Sort of like this. Delete! There we go. And now I'm going to use the distance formula one more time, because once wasn't enough, of course. But you're going to see that it's going to simplify down much, much easier and quicker. So for P and T, so T already have 3 H's minus, say, point P0 squared plus, and then we have a K minus 0, I do believe, squared. The 0 doesn't do anything to it. I'd have 3 H's, which I'm squaring. I get 9H squared plus, and then I'd have a K squared. Again, no fractions. Not that fractions are bad, but it just makes our calculations so much easier when we don't have them. So now let's do it with S and R. So here I've got an H minus R is 4 H's, which we're going to square, plus, and then we have a K minus, I think, 0 squared. This gives me a negative 3 H's, which we're going to square, which is still a 9H squared. And then K minus 0 squared is K squared. And then the rest of the proof is perfectly fine. We don't have to change anything. So sometimes when you think ahead like that, if you have to find midpoints, you're going to be dividing by 2. If you double your coordinates first, so that you have 2's already in there, whenever you go to use the midpoint formula and you have to divide by 2, no fractions. Okay, so that concludes our first coordinate proof. In the next one, we're going to formally try to prove the mid-segment theorem, also with a coordinate proof.